Welcome to the Deep Dive. Our mission, as always, is to give you that shortcut to being well-informed, to really get into the source material so you don't have to. Today, we're taking on one of those huge ideas in popular science. For years, dopamine has been the brain's, its big celebrity, the ultimate gas pedal.
Oh, absolutely. It's the molecule for motivation, for reward, for that constant push for more.
Right. When we talk about learning or building a habit, we always picture dopamine just driving you forward, pushing the accelerator. But what if that's not the whole story? What if dopamine's most important job isn't about hitting the gas, but about fine-tuning the brakes?
What if it's the master architect of the brain's silence?
That's what this deep dive is all about, the incredible architecture of that silence. Okay, let's unpack this. We're digging into a really fascinating study that turns this whole more is better idea on its head.
The research comes out of the Wrocław Medical University, and it was published in Progress in Neurobiology.
And it was led by Professor Jerzy Mosser-Mess's team, specifically work by Dr. Petrais Jabrustak and Dr. Katarzyna Lebeda. So our mission today is to figure out how these D1-type dopamine receptors, we'll just call them D1Rs, how they don't just, boost everything, but how they specifically control the learning ability of the brain's inhibitory system.
And they're looking right in the hippocampus, which is, of course, the absolute core of memory.
This is a huge shift in perspective.
It really is. The brain doesn't work best when it's just firing on all cylinders.
Wow.
You can think of the hippocampus maybe as a recording studio.
Okay.
You absolutely need silence. You need precisely dosed inhibition to filter out all the noise so that memories can actually sharpen and stick. Otherwise, it's just static.
And the Wrocław researchers, what was their key insight?
Well, the most surprising thing wasn't that dopamine affects inhibition. And we sort of knew that. It was how selectively it does it.
So it's not a global dimmer switch?
Not at all. It's a local architect, a meticulous one, making sure the right inhibitory brakes are in place at exactly the right time.
All right, let's get into the groundwork. The study zooms right into the CA1 region of the hippocampus. This is where the principal output neurons are, the pyramidal cells, or PCs.
And these PCs are controlled by inhibitory synapses using GABA, the brain's main stop signal. The researchers started by just listening to the baseline chatter.
These are the miniature inhibitory currents, the MIPSCs.
That's them. Just the spontaneous background conversation happening at these connections.
And right away, this is where it gets really interesting.
It is, because you get the first clue that dopamine is a complex regulator, not some simple booster. When they used a chemical to activate the D1 receptors, an agonist.
You'd expect things to get more exciting, right?
You would. But the strength of the inhibitory brake signal in those pyramidal cells, it actually increased.
Hold on. That is completely counterintuitive. If dopamine is the go signal, activating its receptors should, help things go. But here, hitting the dopamine gas pedal makes the brake stronger.
It does, which tells you that D1Rs are deeply involved in just maintaining the basic structure of inhibition. They also saw a slight increase in frequency, which suggests a little nudge on the presynaptic side, but the main effect was on the postsynaptic side.
It's strengthening the brake pads themselves.
Exactly. And the flip side was also true. When they used an antagonist to block the D1 receptors, the baseline inhibition got weaker.
So, under normal conditions, D1Rs are constantly working just to maintain a healthy level of braking power on these crucial memory cells.
Precisely. Its default job is to make sure the memory circuits don't just run wild, that they stay focused.
And you mentioned it was complex.
Oh, very. They noticed that activating or blocking the D1Rs changed the kinetics of the signal, basically how long the stop signal lingered. It's a technical point, but a really critical one.
What does that suggest?
It suggests that dopamine is physically rearranging the machinery, maybe swapping in different types of GABA receptors that hold on to that inhibitory signal for just a little bit longer.
And they confirmed the mechanism behind this.
They did. They showed that this strengthening effect was blocked if they inhibited something called protein kinase A, or PKA. That confirms it's the expected D1R signaling pathway doing this very unexpected job.
Okay, so that's the baseline. Now let's move to actual learning, to plasticity. This is where the real insights are.
Right, now we're talking about inhibitory long-term potentiation, or ILTP. It's just a way of saying the long-term strengthening of that inhibitory brake.
And they induce this in a clever way, right? not by directly stimulating the inhibitory cells.
Exactly. They used what's called heterosynaptic plasticity. They gave a quick pulse of NMDA, which excites the go side of the circuit, the glutamatergic side, and used that burst of activity to trigger a long-term change at the nearby stop synapses.
So excitatory go activity is actually what tells the inhibitory stop system, hey, you need to get stronger for the future.
That's the one. And in the control condition, it worked perfectly. The pyramidal cells showed a really robust ILTP. The brain learned to tune its brakes harder.
But then they added the dopamine modulators.
And this is the core discovery. This is what Dr. Labida's team really emphasized. It's all about nonlinearity. The system needs a perfect, optimal level of D1R activity. Too much or too little, and the whole learning process just fails.
It sounds like walking a tightrope. So what happens if that dopamine signal is too weak?
It's worse than just failing. When they blocked the D1Rs, the plasticity didn't just disappear, it actively reversed. Instead of strengthening inhibition ILTP, it induced inhibitory long-term depression ILTD, a major weakening of the brake strength.
Wow, that's a catastrophic failure for memory. If your dopamine signaling is too low, you don't just fail to install the right filter for a new memory, you actively start tearing down the filters you already have.
It's a total loss of regulatory control. But, and this is just as critical, the other side of that coin is just as bad. When they strongly activated the D1Rs with the agonist, they also messed up the process.
For too much is also a problem.
It is. It didn't flip to depression, but the amount of strengthening was significantly reduced.
So the big conceptual takeaway here is that dopamine isn't some simple learning booster. It's a condition setter. It literally defines a window of plasticity.
That's the perfect way to put it. If dopamine levels fall outside that very narrow optimal band, the hippocampus just loses its ability to tune its inhibitory network. The recording studio is either too noisy because the brakes are shot, or it's too rigid because the brakes are already slammed on and can't adapt any further.
Okay, so now we have to add another layer of complexity. The brain isn't just one homogeneous block. Inhibition is handled by all these specialized cells, right? These interneurons.
And the researchers used optogenetics tools that use light to look at two really critical types: carvalbumin interneurons, or PV cells, and somatostatin interneurons, SST cells.
And these do different jobs.
Very different. Think of PV cells as the synchronizers. They're fast spiking. They control the rhythm and timing of the main pyramidal cells. The SST cells are more like input gatekeepers. They regulate the dendrites where signals are received.
This is where that local architect idea really comes into play then.
It really is. Let's start with the PV input onto the pyramidal cells. Now, what's interesting is that at baseline, activating or blocking D1Rs didn't really do much to this specific connection.
Oh, that's different from the overall effect we just talked about.
It is. It tells us D1Rs don't necessarily control the day-to-day firing of the PV brake,
Yeah.
but they are absolutely essential for the long-term upgrading of that brake.
So what happened during plasticity?
The ILTP, that massive strengthening effect, was completely dependent on that optimal D1R level. If you blocked the D1Rs, you didn't just stop it, you converted that strengthening into a sharp depression, a major weakening.
And too much activation.
Same story. Strong D1R activation completely abolished the strengthening, dropped it almost to zero. So for this PV synchronization pathway, that fine-tuning window is incredibly narrow. Any deviation, and the whole mechanism collapses.
That's profound. If the PV cells can't properly regulate timing, the whole memory trace could become a mess. So what about the SST interneurons, the gatekeepers?
Here, they looked at inhibitory signals coming onto the SST cells themselves. And again, at baseline, the D1R drugs didn't have a major effect. But when they tried to induce plasticity, ILTP, the system was extremely vulnerable.
Even more so than the PV cells.
It seems that way. The window of plasticity appears to be even narrower. Blocking the D1Rs, again, converted the successful strengthening into depression. But here's the kicker.
Okay.
Activating the D1Rs with the agonist also converted it to a slight depression.
So for these cells, any deviation from the perfect level is damaging.
Right.
Both too much and too little cause the system to fail and weaken.
Exactly. It confirms dopamine's role here is purely regulatory. It has to be in that sweet spot. It's a switch that either permits or denies plasticity, but only when it's set perfectly.
Okay, so we have all these electrical functional changes. The currents get stronger or weaker. But for a change to be long-term, something physical has to happen at the synapse, right? We need to connect this to the actual molecular architecture.
You do. If you want a brake to be stronger, you need to, say, bolt on more brake pads.
So what's the molecular equivalent of the bolt? The anchor.
It's a scaffold protein called gefrin. Its job is to organize and stabilize the GABA receptors, to hold them in place at the synapse.
And the researchers could actually see this happening.
They could. They looked at the SST interneurons, and the results were the perfect structural proof. When ILTP was induced normally, the physical size and density of these Gefferin clusters, the anchors, went up significantly. The synapse literally grew bigger to hold more breaks.
But not when dopamine was out of whack.
The moment they added either the agonist or the antagonist, that physical growth was completely abolished. The functional failure to strengthen the synapse was perfectly mirrored by the failure to do the necessary physical rebuilding.
So D1R activity is like the construction permit. It determines whether the cell even gets the green light to physically renovate its own inhibitory structure.
That's a great way to put it. And there was another cool nuance. If they applied the agonist by itself without the learning signal, they actually saw an increase in Gefferin size.
Even without an electrical change.
Right. It suggests D1Rs might be involved in some kind of pre-assembly or priming process, getting the anchors ready so that when the real learning signal finally arrives, the physical change can happen very, very quickly.
Okay, so what does this all mean? Let's pull back to the big picture. How does this kind of subtle, cell-specific regulation change how we should think about disease?
I think this represents a really crucial paradigm shift, especially for clinical neuroscience. We know that disorders